Okay. Any questions before we get started? Okay, so let me just say a couple of things about the homework that's due next Friday. As is usual in this course, you can always assume that brings have one, unless I tell you specifically otherwise, and that modules are unitary. So when you have the one in the ring times something in the module, it's still M. Okay, so the first one is show that R is commutative in this case with identity. M is an R module. Show that there is an isomorphism from home sub R, Rm. This is isomorphic to M as R modules. Now remember what this is. These are all homomorphisms from R, and R is a module over itself, right? Into the module M. See if you can show that isomorphism there. And let me give you a little hint. The fact that R has an identity might be useful here. Number two, let R be a commutative ring with one. Let M be some R module, and let little m be an element of that module. So we define this subset of R to be I sub M. This is all the junk in R that kills M, right? Show that this is an ideal of R. And just as kind of a notational thing, of course, notice that zero always does the trick, right? And so IM might be just zero. If IM is not zero, if there's some actual stuff that's not zero that kills that element M, then we say little m is a torsion element. If you've ever heard that terminology, torsion. And number B, if R is a domain, show that the set of all torsion elements forms a submodule of M. This is actually important, and we'll come up with classification of finitely generated modules later. And you all saw the fundamental theorem of finitely generated abelian groups, didn't you, in the first semester? This is actually it might not have been couched this way, but this is important there. Show that the set of torsion elements forms a submodule of M, and show me why this may not be the case if R is not an integral domain. By the way, when I say domain, that's me being sloppy for integral domain. Number three, let F from A to B be an R module homomorphism. Show that F is an isomorphism if and only if there's an R module homomorphism G from B to A, such that FG is the identity on B and GF is the identity on A, right? Actually, this is something that you know from set theory. The only thing really to show here, the big sort of meat of this problem, if you will, is showing that that inverse function G that you would just get from an isomorphism of sets is actually an honest to goodness bona fide R module homomorphism. That's really what's the important thing here. This is actually kind of one of my favorite problems. Suppose you have a function that is an R module homomorphism from A to A, and suppose it's got this property. That is to say, sometimes we say that F is an idempotent transformation or an idempotent R module homomorphism. So when you do F of X, it's the same thing that you got as F of X. So you start with X, you do F of X, you keep applying F to that, and you're sort of stuck. It's always the same. Show that A is isomorphic to the kernel of F, direct sum of the image of F. This is kind of a cute little problem. So maybe you'll have some fun with it. So you'll have lots and lots of fun this weekend, singing my praises for giving you such a fun problem. And finally, show, this is actually kind of an important, I think, problem. So notice that a Q is something that might have showed up in linear algebra, right? Q is a Q vector space, right? Everybody okay with that? What's another vector space over Q? Well, Q sum Q, right? 2 copies of Q or 3 copies of Q or a bunch of copies of Q. The reals is a Q vector space, right? Do I agree with that? Actually, because add 2 reals, you get a real, and you multiply a rational number times a real, you get a real. So it's an honest to goodness. The reals is a Q vector space. And actually, from that perspective, you can realize the reals as a direct sum of a whole bunch of copies of Q, and we'll get to that later. Z, can't do it. You cannot make Z, of course, Z is an abelian group, but there's no way to put a scalar multiplication from Q on Z that makes it into a unitary R module, right? And this is very kind of important example. So play around with that, and you will see that even though Z is an abelian group, you can't turn it into a Q module. You cannot do it in a non-trivial way. There's no unitary way to do it. Okay, any questions? So have some fun with that, and let's see here. We will move right back here. Oh, there's that. Okay, so let's kind of get back to where we were last time. The last thing that we had was that so from last time here, we had that home this is the set of phi from M to N such that phi is an R module homomorphism. So that was a notation that we introduced last time. This is always a abelian group. Under pointwise addition of the functions, that is to say, if phi and pitchfork are elements of home R M N, well, when I add these two animals up, it still needs to be a homomorphism. And how do I define this? I define this. One of my sort of central things in math, if you have me for a class before, is if it ain't easy, don't do it, right? I mean, math scares a lot of people, but usually you should do what comes naturally. How do we define this new function that's the sum of the others? To plug in M to this animal, to plug it in separately and add them up. This turns this into an abelian group, right? And if R is commutative, then home R in N is an R module. So let me and how do you do this? Well, if R is in R and P is in is a home, then I need to define R phi. This needs to be a homomorphism from M to N. So how does this new homomorphism function? How do you plug in an N to it? Well, I've got something I can plug in into. It's that, and then I multiply it by R. Right? That's the rule for my new R phi. Let me ask you this. I made this statement here. If R is commutative, then this is an R module using that scalar multiplication. So what's can somebody tell me what the problem might be if R is not commutative?
Like have a number S in R and you plug S M with this R phi, then it might not swap, so the energy would go outside.
Boy, you put your finger right on it. That's good. Absolutely. So her point is this: if S is in R, we need for this to be an R module homomorphism, we need that's what we need to happen, right? Because remember, in an R module homomorphism, you need to be able to suck the scalars out in front of the map, and the map is the whole R phi. Everybody agree with that? That's the problem here. But the only thing that I know I can do is this. And to make this work, I have to be able to swap this S and R, which if the ring is not commutative, I might be in trouble. And that's why I added this caveat about commutativity. There's a danger there, and I really need that. Okay, any questions on that? Okay, so we've defined this. This is another kind of important R module, at least in the case that R is commutative. Let me give you the following definition, which I think will probably not be a surprise to anybody. Whenever you define a structure in algebra, you almost always follow up with, and I'm sorry, this is 1A. You always follow up with the substructures. So I want to define, and I'll do this in terms of left modules here. What do you suppose it means, or what do you want it to mean to have a left submodule? Okay, good. Right. I mean, what I think when I think sub is I think of like, M is the mother and the submodule is kind of a little baby inside there. And what does it mean to be a baby? It means it's kind of a copy of mom in the following sense. Let N and M be a subgroup. So you started with exactly the right thing. Modules are first and foremost abelian groups. And so you take a subgroup, we say N is a submodule of M if if it acts like a vacuum cleaner, as any good submodule could. Equivalently, Rn is an element of N for all R and R, N and N. So what this is it's a little subpiece of M that itself is a left R module. Of course, I can always think of two examples of the submodule of M, namely M itself and 0. Those will always work. Just like I gave you sort of a one-step test for determining R module homomorphisms, I'll give you kind of a one-stepper for determining submodules. And you probably saw the analog to this in 851 for groups. So following proposition. Let R be a ring and M a left R module. So I'll only worry about multiplication on the left here, but I mean, if it's a module, you can multiply both left and the right. Then M is a submodule of M if, actually I won't say if and only if, yeah, I didn't say. N is not the empty set, so I'll have to avoid that silliness there. And X, Y, N, R, and R. Right. So little n, the subset of M is a left submodule if and only if, okay, let's throw out the silly case where n is the empty set, because in these algebraic structures, we don't ever want to have to be the empty set. And for all X and Y and N and R, that crazy sum has to be an N. Proof. This one's pretty easy, right? If n in M, and of course it's not the empty set, is a submodule, and X, Y is in N, and R is in R, then RY is in N, because it's submodule. And X is in N, because I said so. And so therefore, since modules are closed under addition, we got that. Notice I really kind of do need then it's not the empty set, because otherwise the statement's vacuum and true, right? So I do need that a little bit there. The interesting part is this condition is enough to give you that it's a submodule, right? So suppose that n is a non-empty subset, and we have that this condition holds. Well, what do we need? We need it to be a subgroup, right? In to see that n is a subgroup, suppose x, y is an n, we need to show x minus y is an n. Right, that's the subgroup criteria. Everybody agree? In this case, note that what we can do is we can take R to equal -1, right? And so what we have proved is if you have any two elements, X and Y and N, then X minus Y is still an N, and that means it's subgroup, right? What else do we need? We need the vacuum cleaner property. We need this. We need that Rn is an N for all R and R, N and N. So let R N R, Y be an N, and X equals 0. And of course, 0 is an N. Notice that X plus R Y equals 0 plus RY. So it's a submodule because we've also got this as well. Okay, any questions on that? Yes.
Why is X minus Y make it an N, make it a subgroup?
Right, so let me remind you about that. So let G be a group. So I'm gonna couch it in the way that you might have seen this in the first place. So tell me if this is familiar or not. Let G be a group and H and G are this way a non-empty subset then H is a subgroup of G if and only if for all X, Y in H, X, Y inverse. Does that ring a bell? That's subgroup. And so the X minus Y is just translated to abelian. This is the same thing as this. Is that okay? Okay. So for example, this is a rather silly example, but I'll record it anyway. Let M be a Z module. So equivalently an abelian group, right? Then any subgroup so really this is a way to make yourself sound fancy if you're out to dinner with friends, because this really kind of says nothing in a certain sense, because M is a Z module, translation M is a abelian group, then any subgroup is a subgroup, right? Because any Z submodule of M. But check this out and see how this, I like this example just because it helps us come full circle with the definition. Okay, here's a kind of a better example with more juicy stuff to it. Example 6.1.11. Let F A to B be an R module homomorphism. The kernel of F, and let me remind you what this is. This is the analog of what you've seen in group theory, what you've seen in linear algebra, only they would call this the null space or something like that. The kernel of F is the set of A, all the stuff in A that goes to 0. It's just all the stuff that F kills, right? This is called the kernel. And this, let me point out, is of course by definition a subset of A, is an R submodule. All right. Additionally, the image of F, right? This is all the stuff that can be reached by this homomorphism. So it's just everything that's in the image over here inside the target B. This is of course a subset of B is our submodule of B. And in fact, I'm going to generalize kernel a little bit. Suppose that C is a submodule of B. I really should say R submodule, but I'll press that notation when I think it's clear, but ask me if it's not. So suppose I have a submodule of B, then F inverts C. And what do I mean by this? This is all the garbage in A that ends up in C is a submodule of A. Okay, so let's prove something. How about the last one, right? Because if I prove the last one, I get the first one for free, don't I? Because what is the kernel of F? It is F inverse of 0. Everybody agree with that? So this is sort of better than just doing one. So let's prove this. A such that F of A is known as C is an R submodule. Okay, and you know what? It's just like I got a brand new car. I want to get out my new criteria and check it out, right? So first of all, I need to convince myself this is not empty. This is not the empty set. Can somebody tell me why that's the case? For sure, no matter how you cut this pie, 0 has to be in there, right? Because if you look at 0, F of A is 0, right? When you take F of 0, it's got to be 0. And I don't care what submodule C you're talking about, 0's got to be in there. So no matter how you cut it, 0's in there, so it's not in. So I get that. Now let X and Y be in F inverse C and R be in R, right? All we need to do is let's consider X plus RY. Right. Now, of course, I hope that this is in F inverse C, and there's a quick way to test it. F of X plus RY. Well, because F is an R module homomorphism, this is the same thing as F of X plus R F of Y. And because X and Y are in F inverse C, this is in C and this is in C. And since C is an R submodule of B, this whole thing is in C. Therefore, X plus RY is in F inverse C, and we're done. It's a submodule. Okay. Any questions on that? Okay, so here's another important way to form submodule. I'll give you the following example, really. Let X be a subset of some R module. I'll call it A. So let A be some R module that you happen to encounter in your life. And X and a subset, any subset you like, it can even be empty. I'm okay if this X is the empty set. Then the submodule generated by X and I'm going to use the notation here with a little pointy brackets thing. This is, so what is the submodule generated by X? Well, so here's what you hear sometimes philosophically. It is the smallest submodule of A that contains all the crap in X, right? So it could be all of A, right? But it might be something lesser, right? So for example, if X consisted only of the 0 element, I would expect the submodule generated by 0 to be 0. Everybody agree with that? How do I formalize this being the smallest submodule of A that contains all the elements of X? Anybody want to take a stab as yeah.
The intersection of every submodule containing X.
Correct. Yes. So just take every submodule. So M submodule. So what you do is you go through and you collect every single submodule of A that actually contains that set X, and you intersect them all. The intersection of a submodule, I'm crossing my fingers here, I hope is a submodule. And of course, the intersection, if they all contain X, will contain X. And in a certain sense, that'll be the smallest. Everybody agree with that? Let me make a couple of notes. Sort of for the workaday mathematician. So if X happens to take this particular form, the union of I and some index set, some BIs, where the BIs are all submodules of A, then this module that's generated by X is often called the sum of this. As the sum of the BIs. And I'll give you kind of a special case here. If I so the important thing just to take over here is I'm just saying that I is a finite index set. Then that is to say, it's easy to check, by the way, we're going to talk about this a little further, but it's easy to check that if all these BIs are submodules, then the sum is. And what do I mean by this? This is a collection of things that look like little b1 plus little b2 plus little bn, or BI is in capital B. It's easy to check that that's a R module as well. Okay. And also, by the way, let me ask you this. I did say at the beginning of this that I would even consider it acceptable for X to be the empty set. What is the submodule of A generated by the empty set?
The zero.
That is correct. Because what do you do here? You intersect every submodule of A that contains the empty set. Now, I don't know much, but I do know that every set contains the empty set. Agreed? So let me translate that again. Intersect every freaking submodule, right? All of them. And the zero submodule is contained in every module. So when you intersect them all, you'll get zero, because zero is one of the intersectors and it's contained in everything else. Right? And of course, if X consists of a finite set of elements, just a, not even a finite sum of modules, finite set of elements, then let me make kind of another note here. So now I'm not even saying that it's the union of a finite number of submodules. I'm saying it just consists of a finite number of elements. Here's kind of a very workaday way to do it. Then the submodule generated by X is, I think, what you would think. It's all the stuff that looks like this. R1, X1, R2, X2, Rn, Xn, Ri and R. And well, and we know what Xi is. Okay, any questions? So it's almost embarrassing, but I will help us get over this embarrassment. But after being graduate level algebra for a little bit over a semester, I'm going to finally tell you what an algebra is, right? It's kind of embarrassing, but let's. How many of you have ever heard the expression like an R algebra or something like this? Well, let me tell you formally what this is. I am going to start with a commutative ring with identity. And as I give you this definition, you might ask yourself, what is this? Oftentimes when you see general definitions like this, what's happened in algebra and also in mathematics in general is somebody has seen something that's neat and groovy cool that they can use a lot and they're generalizing it. So tell me what you think this generalizes. So I'm going to start with a commutative ring with one. An R algebra is a ring. An R algebra A is a ring. And it's got kind of a special intimate relation with the ring R in the following sense. There is a homomorphism with a homomorphism of rings F from R into A. And let me emphasize here because it's important. I want that F, when you take the when you do F to the one element of R, you should get the one element of A, because A is also a ring, which of course I assume has an identity. Such that notice I said that A is a ring, so I'm assuming that it's got identity, but I don't assume it's commutative. I don't know if this is standard notation, but I don't do non-commutative stuff. So what we're saying is the image of the ring R goes into the center of A. And the center of A is just all the stuff in A that multiplicatively commutes with everything. Right, the center of A is all the stuff in A that commutes with everything else in the ring. All right, that's like so let me ask you this. Anybody, what do you think this is mimicking? I'm going to give you what I consider to be kind of the blueprint, the prototype example of this. Anybody know what somebody's trying to mimic by doing this? Am I going to have to call on Morpheus here? You guys don't watch enough movies. Here is one of my favorite examples. Oops. Take any commutative ring with identity. Z, Q, any commutative ring with identity. Let M in R be the collection of all n by n matrices with entries in R, right? Notice that this ring of matrices is a ring, right? You add two n by n matrices, got an n by n matrix. You can multiply two n by n matrices. It's a terrible math, right? It might have zero divisors and all kinds of, might not be commutative, but it is a ring. Can anybody explain how F, so we need this F from R into, in this case, M in R. Okay, my output needs to be an n by n matrix. That's exactly right. Which is, if I had been smart, I would have written it this way, where I represents the n by n identity matrix. Right? Notice that F of R is contained in the center of M in R. Because if you have X times the identity matrix, anything in F bar times any other M by N matrix, let's call this matrix H, but let's just call this B. Well, the identity matrix and scalars both commute with the matrices, or every matrix. So this is B. So this is exactly what we need. So this is, to me, this is kind of a prototype example of an algebra. Take a ring, a prototype example. Of course, there are much easier examples, right? So for example, with this particular definition, if you have any commutative ring with identity, if A is another commutative ring that contains R, then it's an algebra, right? And the homomorphism that you would have to use here is much easier. It would just be the inclusion homomorphism. Okay, any questions? Okay. Right, so let me give you one last definition in this section before we move on here. Definition. let's suppose that A and B are R algebras. So these are both algebras of the same ring, of course. Then it probably makes sense for me to try to tell you what it means to be an R algebra homomorphism, right? We talked about homomorphism of rings, modules, groups. What is an R algebra homomorphism? We'll call it B, main B. Is a, we'll see A and B are rings, right? Because any R algebra is a ring. So I want this to be a ring homomorphism. Such that, number one, now I've 99 times out of 100, I assume this with any ring homomorphism anyway, but I'm gonna emphasize this here because I absolutely demand this for an R algebra homomorphism. So I need to take the identity of the ring A to the identity of the ring B. And I also want this to be an R module homomorphism. That is to say, phi of RA is R phi of A. For all R and R, A and A. This is so it's a ring homomorphism, but at the level of R, it's also an R module homomorphism. Okay. Any questions? Okay, so now I'm going to move on to quotient structures and the homomorphism. Now, one of the coolest things about algebra is there's lots of kind of themes that are repeated over and over again, right? Well, what did you have? You learned what a homomorphism was for groups, right? And then you get all these homomorphisms, first isomorphism, second isomorphism, et cetera. Same business for range, right? Well, now we're going to get this for modules, and a lot of this will be basically, remember, modules are first and foremost abelian groups. So really, all that R module homomorphisms in the structure terms are going to look very much the same as to what you're familiar with. They've just got that little extra sprinkling icing on top with this business with the scalar multiplication from R. Let me begin with the following theorem. Let's let B and C be R submodules. So that is to say, A is an R module, and B and C are R submodules. Okay? Then A, the closure group, A over B is an R module. Now, see, we get a lot of the stuff here for free. The first thing I get for free is the fact that this is actually, we know that the quotient of these two groups is a group, right? A and B are abelian groups. Any subgroup in abelian groups normal, so this makes sense. All I've got to do to convince you this is an R module is tell you how R acts on it. Remember, folks, if it ain't easy, don't do it. What should R times this be? Right. Better be easy. The map from A to A mod B given by pi of A is equal to A plus B is an R module homomorphism. In fact, I didn't say it here, but is an R module epimorphism. With kernel B. C, there is an R module homomorphism. B intersects C is isomorphic to B plus C minus C. And D, if C is in B, then B mod C is in A mod C. And what is more, when you mod them out, this is isomorphic to A mod. That is enough for now. Any questions on this? Yeah, before next time, just for giggles, you might think about how the proofs work. They work exactly like Matt probably showed you last semester, with just a little bit of extra. So think about that and we'll discuss that next time. Y'all have a good weekend. This is a long weekend, so I'll see you all Wednesday. Have a good one.